And there I am. Yeah, I need to line it up. About like that. Okay. And it's recording. Check the sound level. Audio. Okay, that's good. Video settings. That's good there, and that's good there. Okay. Now, unmute. There we go. All right. Next on the agenda is thermochemistry, which should have something to do with heat. Just a little review. The universe is made out of basically two things, energy and matter. Now there's some argument as to whether there's some dark energy and dark matter, but since there's no direct evidence, we'll dispense with that one. Energy itself is a measure of the capacity to do work. And then we have to define, well, what is work? Well, produce heat, of course. Let that out. Energy will either do work or produce heat, or sometimes both at the same time. So what do we mean by work? Well, in physical terms, work is a force applied through a distance. That is, something has to move under a force. Otherwise, there's no work done. So if I stand here and push against this wall, I'm not doing any work because the wall's not moving. But I am expending energy. So that means that if I'm not doing work, then all that energy I've expended is being shunted off into heat. So it's either one or the other. You're either doing work or you're generating heat. Now, the law of conservation of energy just says that energy can be converted from one form to another, but it cannot be created, cannot be destroyed. So energy can come in several different forms. It can be electrons moving down a wire, or it can be an atomic blast, which is actually a combination of energies. You get light coming off, that's the first thing you see. Then you get actually a direct result of that light. The light from an atomic blast occurs in a whole spectrum from gamma rays all the way down to infrared. And the infrared part is what heats up the atmosphere, and that makes the blast. Other types of energy, I think we're going to talk about that in a minute. The thought just crossed my mind, but I don't want to steal my own thunder. Another concept that is stated like that, actually this is universe. Total amount of energy in the universe is equal to the change in the total amount of energy in the universe is zero. It's constant, doesn't change. That's the first law of thermodynamics. Now we can also subdivide energy into two different types. One is kinetic energy. We'll take it first. We might have mentioned that one already. Kinetic energy is energy of motion. So if something is moving, it has mass, it's got kinetic energy. I usually abbreviate it this way. So if you know the mass of your object and how fast it's going, you can calculate its kinetic energy. You can do that with elementary particles, or you can do it with planets. It doesn't matter. Now, potential energy is the energy that has not been realized as kinetic energy. And it can come in either based on its position in a gravitational field or on its composition, that is energy stored in a chemical bond, for instance. So if I were to climb up on this building, I would have to add energy, potential energy, expend some sort of amount of energy to get me from this level to that level. And that energy would be stored in my position. And I could get it back, I'd jump off the building, but when I hit the ground, I'd be going at a certain speed and have kinetic energy. And then when I hit the ground, that energy would be turned into heat, or it'd be used to break bonds, like the ones that are holding my bones together. Okay, so this is just an illustration of positional potential energy. The potential energy of this ball A is greater than the ball B, because it's higher. So if we release that A and let it hit B, theoretically, it would transfer enough of its energy to get B up to its height. Now, that's theoretical. What actually happens is only some of the energy is converted into positional energy for B. The rest is consumed by friction, which means it's converted into heat. But the total amount of energy that A had up here is still the amount of energy that is in the universe. Okay. All right, now let's talk about a specific type of energy called heat. We measure heat based on its temperature. So we need some sort of a thermometer to measure what the temperature of an object is. And if we know some other characteristics, some factors involved in that object, we can tell how much heat it contains. But in order to do that, and in fact, to measure any kind of heat, we measure a difference in temperature. That is, a transfer of heat from one place to another involves a change in temperature. So if my skin is like 97 degrees or 96 degrees, and I pick up an ice cube, it's going to feel cold because heat is being transferred from my hand into the ice cube, and my nerves sense that. It's a change in temperature in my skin. Heat has been transferred. Well, I already mentioned this one. Work is force acting over a distance, so W equals F times D. And of course, I'll mention oops. Let me start the crap out on me. See if this one works any better. Work. So force acting through a distance. Usually the units of measure here are standardized. Right? So mass will be in kilograms, and velocity will be in meters per second. Right? So if we square that, energy then is kilogram meters squared per second squared. Right, that so it can be. There we go. Now those are the actual units of kinetic energy in this case. But we have a special, we reduce those into a special unit called joules. One of these is 1 joule. So if we're going to be able to convert one to the other, we've got to be sure that the units of measure are the same. So this work is also going to be measured in joules. So that means the total, this times this, has to be that. Right? So this force times the distance, which will be meters, should be joules. And the force is a special unit called newtons. So we can deduce from that newtons is actually going to be kilogram meters per second squared. Because then if we measure this, multiply that times that, we get the meters squared out of it, and then we're back to joules. So that's what a newton is equal, kilogram meters per second squared. You get a little physics for free today. Let's see. Oh, okay. The next topic that always tends to come up is what type of function are we dealing with? A state function is a description of a system that does not depend on how it got there. It's just its state at the moment. So anything that describes a system in terms of where it is right now is a state function. Only depends on the present state. That's what it is. Okay. So if that's a state function, then there's probably a function that depends on how it got there. We call that a path function. Because the path the object took does have an influence and does, but there's a dependence of the object and its path, how it got there. Let's see. I thought I had a slide on that one, but I don't. For instance, how much heat does an object contain at the moment? Okay, you need to know its temperature, you need to know its mass, you need to know its specific heat, and you can tell what its state is at that time. But the path, suppose, let's see, what's a good example? How much energy would it take to get me from Charleston to Beckley? Okay. The change in elevation is like almost 2,000 feet. Actually, it's about 1,850. It's about 1,850 feet in change in elevation. So I've added energy to my position, but it depends on how I got there. The amount of energy it takes to get me there, if I go on the turnpike, it takes a certain amount of energy to get me to that height. But if I get off the turnpike and say I go through shoot, mine's going blank. Where was it that Tech was located?
West Virginia?
Yeah.
Montgomery?
Montgomery, thank you. If I go on the river to Montgomery and then I go back up through Oak Hill, it's going to take more energy to get me there. That would be a path function. Okay. So we'll let that horse rest and beat it again later. But for now, we're going to define some terms. When we talk about transfer of energy from one place to another, we've got to define what's not the border. Border's in the news, so it's stuck in my brain. What divides, what is the energy crossing to get from one place to the other? What am I trying to say? So we have to define what's our system, and then everything else is surroundings. So when we talk about transfer of heat, or energy for that matter, we define our system as whatever we want it to be, or whatever is appropriate for the chemical reaction we're discussing. And then everything else is surroundings. Okay? Now, those surroundings could be as big as the universe, right? If this is completely open. Or we could isolate the surroundings. We could just wall it off somehow so that we have a defined surroundings and a defined system. Usually, though, we define what the system is in terms of whether it's open, right? An open system will allow transfer of matter and energy. Okay? A closed system will only allow transfer of energy. Boundary. Across the boundary. And this is our boundary. And an isolated system, no transfer of any kind, matter, energy, will not transfer across this boundary. So that system is isolated. Now that's the kind of system we use when we're going to do our calorimetry lab. We have our scientifically designed styrofoam cups. We have two styrofoam cups sit together. We'll cover them. We have a thermometer access. We'll have a stirrer, and then we'll put stuff in there. And maybe it'll undergo a chemical reaction. Maybe it'll just transfer heat from an ice cube to water, whatever. But when that happens, we're calling that an isolated system. In other words, nothing transfers out or in. Everything is isolated inside. And I'll show you how to deal with that mathematically, and maybe today or maybe right before the lab. Okay, so we've defined our systems and our surroundings. So now we can apply some terms to what happens with a system when we allow heat to flow, right? So the abbreviation for heat that we're going to use is a little q, small q. So if heat flows into the system, right, we say that that is endothermic. That is, the heat flows into. Endo is the prefix, the Greek prefix that it's into. So that's endothermic. Notice that everything that we define is in terms of the system. right? So if heat flows into the system, any number that we attach to that is a positive value because we're adding to the system, okay? If heat flows out, that's exothermic. And of course, since heat is leaving the system, that number will have a negative value. Now, the energy that was transferred here, say, into the surroundings, remember, we can't create or destroy energy. So if heat flows in, the heat that flows in here was lost by the surroundings. And the heat that flows out here was gained by the surroundings. Of course, we still have a positive negative here because it's in terms of system. But that's just to say that we can't create or destroy energy. It can only be transferred. So let's see if we've got a grasp of what we mean by endothermic and exothermic. Whenever we think of these terms, we have to be mindful of what's the system and what's the surroundings. So if we have freezing of water, so we have a certain amount of water here, and it freezes. So what happens to the system if it changes state from liquid to solid? It has to lose energy, doesn't it? Okay. So that means it's an exothermic process for water to freeze. Let's see if we can identify these. We're actually told what the system is. So in this case, we're defining the system here as your hand. So your hand gets cold when you touch ice. Right? Exothermic, because the heat has to leave your hand into the ice for you to feel that decrease in temperature. Oops. That happens sometimes, you hit the button. So when ice gets warmer, you are introducing more energy into the ice. That's endothermic. Water boils in a kettle. Endothermic, yep. Water vapor condenses on a cold pipe. The water vapor is the system. When it condenses, the system is losing energy, right? It's exothermic. And ice cream melts, endothermic. Okay. I think we have an intuition about these things. So let's see. Sometimes the conditions of a process just naturally scream, I am the system. Right? So if we have methane burning in a Bunsen burner in a laboratory, what's the system and what's the surroundings? Well, if you think of it in terms of the chemical reaction, the natural gas or the methane comes out and mixes with oxygen. And then you have your system. And it ignites, releases energy, and converts into carbon dioxide and water. So the system in that case is the flame itself. And the room, or all the space around it, is its surroundings. Oops. This one is a little more difficult. Water drops sitting on your skin after swimming evaporate. So actually, we could define it in terms of your skin or in terms of the water. But I think what they're getting at is defining it in terms of the water. The water is the system, and heat is flowing from your skin, endothermic, into the water to make it evaporate. That's why it has a cooling effect on your skin, as the heat's drawn out of your skin to make the water evaporate. That's true. Hydrogen gas and oxygen gas do react violently to form water. So they do this number. And if we're going to, at the temperature that this happens, water's a gas. It's a vapor. So which is lower in energy? All right, now we get to the concept of, first of all, this is the system. Where did that energy go? When you talk about energy that is produced by a chemical reaction, it's helpful sometimes to think of where would we put that energy in this scheme? Like make it one of the reactants or products. Right? So if this is the reaction, then it's producing this plus energy. Right? A change in enthalpy is the term. And we'll get to that in a few minutes. So that means if it's on this side, it's exothermic. Right? It's releasing energy because it becomes one of the products. Now, what does that mean in terms of which one is lower in energy as far as the products go? Right? If you've extracted this energy out here on that side, that means it was over here. Right? Because we can't create or destroy anything, heat or matter. So if it's over here, that means it was in here somewhere, in those chemical bonds. So that means these together are at a higher energy level than this one is. This one's the low energy side. That's the high energy side. Okay? And that is typical of an exothermic reaction. Or any reaction in which the products are lower energy than the reactants. That tends to drive the reaction. Because in chemistry, matter likes to be at the lowest possible energy state it can achieve. Okay, I mentioned thermodynamics earlier. Thermo, of course, coming from heat. Dynamics refers to movement of some kind. You know, change of heat. Heat flows, yada, yada, yada. So heat dynamics, thermodynamics. It can also be described as the study of the energy and its interconversions. That's true. And the law of conservation of energy is often defined as the first law of thermodynamics. And one expression of that is delta E equals 0. In other words, you conserve energy in the universe. You can only change it from one form to another. You can't create it. You can't destroy it. So that's your first law of thermodynamics. Now, concept of internal energy. I mean, that sounds big, but it's really very simple. All you have to do is add up all of the energy in your system. And not outside the system, in the system. And all the energy in the system, whether it's kinetic or potential, doesn't matter which, you have to account for all the energy. Whether it's the particles are moving, kinetic energy, or they are under pressure, or they have chemical bonds, all those together define the internal energy of the system. Now, internal energy can also be a summation of both the heat that's contained in the system and the work that is done on the system or by the system on its surroundings. Okay, so there's a transfer there. This heat is transferred. This work is a kind of transfer of energy. Right. So what do I mean by work? Say if we do work on the system, say it's a confined gas with a piston on it. If you push on that piston, you're applying force through a distance, and the work that you do pushing on that gas is transferring that work to the system, right? So it's positive, it's going into the system. If we let the piston expand, then the system is doing work on its surroundings, okay? If there's a transfer of heat in the process, that will also be incorporated into a change in internal energy. Okay. So, here we go. Oh. Yeah. I need to turn the speaker up. Hope I don't make it too loud. Maybe that'll do. Let's back up.
System or heat dynamics gives the relationship between the internal energy of a system and the energy flow into and out of the system. This example shows a system where heat enters and work is done by the system. Internal energy remains constant if there is no friction. If instead of adding heat, we do work on the system by compressing the piston, then energy will flow out of the system as heat. The internal energy is again constant. Take note of the sign conventions for Q and W. The signs of Q and W are positive when energy enters the system. Here, we have a system in which a chemical reaction is taking place. What are the signs on Q and W in this example? Is there a change in internal energy?
There shouldn't be. See if we got something. We take control. There we go. Okay, this is just reiterating. So when we talk about these quantities, we have two terms, the numerical value and the sign. And sign has special meaning depending on which way the flow is. We already talked about that. So if the heat flows into, Q is positive, flows out of, Q is negative. If the system does work on its surroundings, then the work is leaving the system as it does work on the surroundings, so that's negative. And if the system does work on the surroundings does work on the system, then you're adding work into the system, that's positive W. Now, like we said before, work is a force over distance. So if the force, these terms, we define these terms, F is one term in force, so that would be a force in newtons. Newtons is a force. D is a distance, would be in meters, standard units. But when we talk about gases, and thermodynamics was first investigated using gases. So it's instructive to approach it from this direction. So what's happening with this gas, we don't measure terms, usually we measure our terms as force directly. We usually measure it in terms of pressure. So we need to find a conversion for a pressure that will give us force. Since pressure is a force per unit area, the area stays constant. So under pressure, the only thing that changes is the distance that the piston moves. Right? So we've changed a certain amount of volume by moving that piston. And the area doesn't change because the piston is constant area. let's see, did I put, yeah, here we go. So if work is going to be force times distance, and we have pressure equals force times area, then we solve for force, which would be force equals pressure times area. Then we can substitute P times A in here for that term. So that would be P times A times D. And then if we know that the volume that changed during this process is distance times area, then we have distance that we can solve and get a change in volume divided by area and plug that into the D value. So when we do those substitutions, we get these units, and then they reduce to pressure times change in volume, because A here is in the numerator and A there is in the denominator. They cancel out. So another expression for work in terms of compressing gas as our system is W equals P times delta V, as long as the pressure is constant. Let's see. There it is, P delta V. Now, the problem is when you have a pressure and you multiply it times a change in volume, the change in, let's say, an expanding gas, delta V then would be positive, because the change in volume is going from small to large. And the pressure, of course, is going to be positive, because pressure is constant. It's a resistance to that motion. So that's positive. So those together are a positive value, right? But remember what we said, for an expanding gas, the system is doing work on the surroundings, which means it has to be negative. So in order to maintain our convention, we have to stick a negative sign out here, so that the work is actually negative. We know that this is positive. This is for expanding gas. But you can make the same argument for a compressing gas. In that case, this will be negative, which would produce a negative value here. But for a compressing gas, you're doing work on the system, which means this should be positive. Right? So then that negative makes this positive. Okay? That's just the way things happen. You have to make allowances and make corrections where necessary. This is a conversion factor that should be in useful information. I'll check to be sure. There it is. Just in case you need it. What was that? Liter atmosphere is 101.3. So if you run this up, there it is. About midway down the second column. Remember the value of R? If we're doing pure gas laws, then we use 0.8206 liter atmospheres per mole K. If we're doing calculations where energy is involved, we want 8.3145 joule per mole K. Now, if you set that up at equivalence and solve for joule liter atmospheres, you'll find that liter atmospheres is equal to 101.3 joules. That's why the difference between these two is that conversion factor. And when we do calculations that require R relative to these work functions, we will be using that value. Okay. So which one of these performs more work? Let's see, let me get rid of this and this and this and just stick with our derived equation like that. A gas expanding against the pressure. So the pressure is 2 atmospheres. Okay? And it's going from 1 to 4 liters. It's getting bigger. So that means the delta V is 3 liters. So negative would be -6 liter atmospheres is the work that's been done. See, we haven't converted it to joules yet, but since we've got the same units of measure here for both of them, we can still compare them in terms of the work. So the second one was constant pressure of 3 atmospheres, and we're still expanding. So 3, and then it's going from 1 to 3 liters. So that's 2. 2 liters change. So that's -6 liter atmospheres. The same amount of work has been done by the system on its surroundings. It's negative. The only difference is the pressure against which it's working, and then of course the change in volume. They both come out to the same value. Okay, let's see. I need more room, so I'm going to have to erase this. So let's determine the sign of delta E. Remember delta E, let's get our definitions back up here. Equals the sum of the work, the heat transfer plus the work. Okay? So if we have an endothermic process that performs work, an endothermic process, so that means heat is being transferred into the system. Okay, and it's doing work on the surroundings. Okay. So that means this value is going to be positive. This one's going to be negative. Okay. So what if the magnitude of this one is bigger than that one? That's absolute value. Oops. I'll do it. It's supposed to be a straight line. So if the magnitude of the work is greater than the heat, then this one is more negative than that one is positive. So overall, delta E is negative. Okay. So there's a loss of internal energy in this case. You've lost some internal energy when these conditions are met and that one exceeds this one. The other way around is when that one is less than that one, then the negative is less than the positive, and this one then means that we have added energy, internal energy, to the system. Okay? Is this the first time you've probably seen this before? Yeah. Okay. But this is your first. Okay, so I understand that it can start spinning your head around. So this one right here is just the opposite situation. Work is done on a gas, that way, that way. So these terms will just be the reverse of those. Right? You can do the same logic, just reverse that arrow, reverse this arrow, and then set up these conditions again. And in that case, you would have a positive one here and a negative one there. So this one's going to be positive, and that one's going to be negative for the exothermic process. Okay. Change in enthalpy. Okay. Try to follow me here. I hope I can explain this so that it makes sense. The difference between delta H and Q, they both represent transfers of heat. Right? It just depends on the conditions under which that transfer is made. There are situations, and most of the time, the situations that are created by chemists are such that they are equal. But their definitions are different. Q is the actual amount of heat that is transferred into the system or out of the system. Okay? It's one of the two ways that energy is transferred during most thermodynamic processes. The other being W. Energy is either transferred as Q or as W. Okay, there's the W. And we write it like this. There must be another slide coming up. Yeah, okay. Enthalpy, or H, usually, H is a theoretical term. You can't determine H independent of a change. So you always have to do a delta H, you know, what is it now and what is it afterwards. Refers to a potential. That is, what's the potential energy that can be transferred in terms of heat. And this defines the delta H of a system. Okay, so delta H being equal to whatever the internal energy is of the system, and then whatever change occurs to that value. Notice that in this one, we've pulled that delta out, and it's part of the whole thing. So for this potential energy to be valid, you have to account for a change in internal energy and any incremental changes that occur in pressure volume. This permits us to allow pressure to change as well. And you notice with the former definition of Q, pressure had to be constant in order for Q to work. So, what conditions? Okay, so I'm going to derive it. So let me not talk ahead of myself. So we know what delta E is equal to. It's Q plus W. Right? So if we stick Q plus W in here, right? Q plus W plus this one. That's also equal to the enthalpy, the potential heat energy of the system. Then if we allow the process to take place at constant pressure, That is, we pull this P out and hold it constant while we let the volume vary. Then we get our familiar version of Q. Since this is equal to minus W, and this is W, then those two cancel out. And when that happens, Q and delta H are equal. Right. So usually when chemists conduct experiments, unless they have a compelling reason to allow pressure to vary also, we hold the pressure constant. That way, we can do a measurement of enthalpy simply by measuring the change in heat. Okay, and get a metric for the enthalpy for the system, the potential for the system. So the end story is, if P is constant, delta H and Q are equal in magnitude and units of measure. Okay. Is that the way they explained it at Marshall?
Yeah.
Oh, good. Because I don't know how they do it over there.
They do something.
Okay. Then I'm entirely within my rights to do it weird in my own way. Okay. Actually, if it doesn't make any sense to me, I'm not going to try to teach it to you.
Yeah, I feel like they teach more stuff that don't make sense to them. So interesting.
You know, I got the feeling like when I was a student too.
Yeah, it seems like that sometimes.
Especially when they had an instructor or a teaching assistant that wasn't even born in this country. They have a lot of those.
Yeah, that is true.
We had one, actually he was a professor, one of my physics professors. I think it was second quarter. When I was undergraduate, I was in the quarter system, not the semester system. So we had, his name was Dr. Xu. He was hard to understand. He was Chinese.
Yeah.
So, not to his face, but amongst ourselves, we referred to him as Blue Suede. Anyway. Okay, so for this example, you're studying a process that takes your system from these pressure, temperature, volume values to these pressure, volume, temperature values. You can go, this is a path function. In other words, you can get there by going, let's watch the pressure for a second. So you let the pressure go up like this, and then it goes down. And it goes back up here. It goes back up here. So the overall pressure difference is here, but it took forever to get there by this circuitous route. Those different paths mean that the values of Q and W will be different in the process. Right? So because we let the pressure vary, we let the temperature vary, at the same time the volume, do all these variables, it really, the changes in Q and W do depend on the path that was taken. The interesting thing, though, is that no matter what path you take, delta H, remember, is the potential heat energy of the reaction. And potential doesn't matter how it got there. The delta H is a state function. In other words, that change is independent of how we got there. So that's fortunate, because in that case, all we need to know to find the delta H of the system, of a chemical reaction, is the delta H combined of all the products, and then subtract the delta H for the reactants. just reiterating. If the pressure is constant, then we can say that the delta H and the Q are equal. In that case, the Q will also be equal to the, I should have put a delta here on those. The delta H is for the products and the delta H is for the reactants. So that's fortunate, because now, if we burn propane, we burn propane, this is our balanced equation, and this is the potential enthalpy of the system. So with that minus value, we know it's exothermic, and it's exothermic to this extent, 2,221 kilojoules, right? Which means, well, let's turn this into scientific notation. 2.221 times 10 to the third kilojoules. And then a kilojoule is 1,000 joules. So if we want to put it in terms of joules, we just need 1,000 more right here. 10 to the sixth joules. Okay, so it's a lot of energy out of this reaction. Of course, if you've ever run a propane burner, you know that's true. A lot of energy. Now, the convention is, well, actually the convention depends on who's writing the textbook or the reference manual. Sometimes they put kilojoules per mole out here. And that mole refers to mole, 1 unit of this entire equation when they put moles. I like it if you just say, that's how many kilojoules you get from this reaction. So that many kilojoules per 1 mole of propane, or that many kilojoules per 5 moles of oxygen in this reaction, or in terms of 3 moles of CO2 produced by this reaction. Okay, so then you're free to use any units of measure here as a denominator, depending on what type of conversion you're going to do. So I like just the energy for that reaction out here by itself, and no stated moles to begin with. So the question is, if we have this balanced equation, and we know the delta H, then can we say how much heat will be produced by the combustion of 5 grams of propane? Let's see, do I have that? Oh, there it is. Okay. So remember, we always have to convert to moles before we can do any type of stoichiometry. And this is a type of stoichiometry problem, because energy production or consumption in a reaction, I like to visualize as either one of the reactants or one of the products. It's easy to wrap my brain around that one. So we find out that we are using a little over 1/10 of a mole of propane to produce this reaction. Well, if this is in terms of the reaction and that's 1 mole here, then we can use this in terms of 1 mole of that to convert this one to energy. So the total amount of energy that's available is this times that, and there's your 1 mole of propane, cancels out, and just multiply this times that. And with 5 grams of propane, you get that much energy. Okay? And of course the sign, you always have to be mindful of the sign, is means that it's exothermic. Now, calorimetry, which is what we're going to be doing next week. It's just, we can take the name. Calor is I think that's Latin for heat. And metric is measure. So you just measure heat. And of course, when you do it, you use an isolated system, and you put your components in your isolated system, and let the reaction go, and you measure a change in temperature. There are other factors that have to be taken into consideration, like what's the mass of all your components. Sometimes you need to know individual masses, because usually the specific heat is in terms of the change in temperature of 1 gram, amount of energy required to raise the temperature of 1 gram of substance by 1 degree Celsius. That's the specific heat. And I'm not sure about your textbook, but S is generally the term that we use for specific heat. When I was going to school, we used little c. Yeah. So each one is valid. But it's easier to get this one mixed up with degrees centigrade. So I like to use S now. Now, that's specific heat capacity. Sometimes we refer to this change in temperature, the heat required to change that temperature, in terms of moles, right, rather than grams. And then we call it molar heat capacity. Definitions are almost identical, except for the change from grams here to moles. That's the only difference. Okay, so if we put 2 reactants together, and they're both at the same temperature, and then when we do that, the temperature actually increases, then the reaction has produced energy that leaves that reaction system, those 2 items. Now, we have isolated our system, but then within that system, we can subdivide, right? So they may take place in water. So those 2 reactants produce energy, and they cause the water temperature to increase. That means the reaction is exothermic. And obviously, the converse, if the temperature decreases, then the reaction is endothermic. Hospitals use that all the time, right? When you make a cold pack or a hot pack. Let's see, anybody here work in a hospital? Yeah, right. So if you have, there's something inside that bag you have to break, and then mix it with the water inside. Well, one of the reactions is exothermic at your hot pack, and one of the reactions is endothermic at your cold pack. Okay, so that's what our device will look like. I used 2 styrofoam cups just to be sure the system is isolated, but still, there's the opportunity to lose heat or gain heat through that cover, right? So it's not perfect. But notice that when we stick the thermometer in there and we stick that loop in there, those become part of the system, right? So if the reaction is occurring in here, but these guys are going to either absorb or release heat to the system, depending on whether it gets colder or hotter, we have to take those into account. And even the styrofoam will absorb heat or release heat, right? So we have to determine for this combination of things, we have to determine what is its heat capacity. How does it influence the system, so that we can remove that factor from our final results and isolate. Then we know what actually happened. Okay, that's known as the calorimeter constant. So that's why the first thing that I have you do in that method is determine the calorimeter constant for your construction. Okay, and all you have to do is take some cold water and at a temperature and some hot water at a higher temperature and use the same volume, put them together, and you know the temperature before and after here, and you measure the temperature when they equilibrate, you can determine the constant. Okay. Maybe we'll have time to do some calculations. Let's see. Do I need to give anybody a break? Are you okay? All right. Let me check my times. Stop. Okay. We need it. We got another hour if we need it. Okay, that's our calorimeter. I've used calorimeters that were factory made, but they're not as efficient as this design. Because they're usually made out of aluminum or something like that, and they just really don't. You have to have a large amount of reactants to compensate for all the heat absorbed by that calorimeter. Even though it's a can inside a can, so you have that airspace that insulates it, but it's still not as efficient as this. Like this, you can do it with smaller quantities this way. Okay, so what is the heat change that takes place? That's Q. You have your specific heat, and then you multiply it by the mass, and then by the change in temperature in degrees centigrade. Okay. So that means if this is going to be in joules, this is going to be in grams, this is going to be in degrees C, then in order to cancel those out and leave you with joules on this side, you need joules up here, you need grams down here, and you need degrees C down here. So the units of measure on this one are going to be joules per gram degree centigrade for your specific heat. Okay. Oh, there it is. All right, so this one's easy, the first one. You don't even have to do any calculations. If you've got equal masses of water at these two temperatures and you put them together, what's the final temperature going to be? Well, it's going to be, they're going to meet halfway because they're both water, both the same mass, right? So they have the same heat capacity, and they're going to meet in the middle, which will be 50 degrees. It's when you have different masses that you end up having to calculate the final temperature. Here's how we do it. Our isolated system says that whatever happens inside that system, the total heat that changed inside that system is equal to 0. That's characteristic of an isolated system. Everything we do over here has to equal 0 inside that system. So you've got 1 Q for the, say, the 90-degree water, and then you've got another Q for the 10-degree water, and if we had a calorimeter constant, there would be another Q for the calorimeter. But at this point, we're ignoring that. So you just add up all your Q's, and they have to be 0 in an isolated system. Okay? Now, I know that sounds funny because we just said that a reaction takes place and it generates heat. Well, that's another Q value, referencing that production of heat. Okay? But they all have to add up to 0. Okay, so in this case, we have 90 degrees, so we have the specific heat for water. Oh, we don't have to calculate it. We're doing qualitative analysis now. Right. So if you have 500 grams of water at this temperature and only 100 grams at that temperature, they're not going to meet in the middle, right? They're going to favor the larger mass at this temperature, so they're going to be between 10 and 50. It's going to be on the low end. Okay, so I was getting ahead of myself. I thought I was going to have to calculate something. But I just realized we haven't been given the specific heat of water, so I can't calculate it. Well, why does it say that? Oh, we are going to calculate it then. So here's the specific heat of water. Oh, we're going to use, oh, in this one, we're going to use water and an iron ball. Okay, that's fine. In order to do the calculation for the earlier water, we would have to use this value in here for S m delta T for that one, and then S m delta T for this one. And then the delta T would be, it's always final temperature minus initial temperature for either one. The final temperature for this would be what? That's the one we're solving for. We don't know what the final temperature is, but it's going to be the same for both of them because we wait for them to equilibrate, that is, they come to the same temperature. So then this one will be our unknown. This one will be the 90 degrees, and over here it would be the 10 degrees. And then we would have different masses. I think this one was 500 and that was 100. But the S would be the same. And then you just do your algebra and solve for final temperature. And I think they said it was 23 degrees. Okay. So now for this one, I'll just set it up. The final temperature of the water is going to be something. Let's change your subscripts. So this one's going to be water, sound like thunder. And this one's going to be the iron ball. Okay? So if we set those up for water, we're going to have the S for water, 4.18 joule per degree C grams. And then the mass of the water, which is 50 grams. And then the delta T is going to be the final temperature, which will be the same for both of them, minus our starting temperature at 10 degrees. Okay? Then we add the one for iron, 0.45 joules per degree C gram. Notice that the heat capacity for iron is almost a tenth of what it is for water, which means that for the same amount of heat added to the same mass of iron as water, the temperature is only going to change a tenth as much. No, it's going to change 10 times as much. 10 times as much. So the heat capacity, the lower heat capacity will have a larger change in temperature. Okay, so let's fill in the rest of it. So what's the mass? 50 grams. And then we have, I'm going to pick up the board over there. Yes. 50 grams, and then the final temperature minus what was the initial temperature? 90 degrees. Okay? So that's where the negative sign comes from. Right? We're going to have this heat and actually minus this heat because of that negative sign. So if you resolve all of this stuff together, you find that the final temperature equals 18 degrees centigrade. So do you think you would have any trouble solving this equation? You just say this one times that one times that one minus this one times that one times that one. Right? When you expand it. Do we need to do that? Maybe we should.
Just be safe.
Okay. All right. So what we're saying is now 0 equals, let's see what this is right here, that part. 4.18 times 50. And that's 209. So that would be joules per degree C, because the grams are already canceled. Then you multiply this times that. So that's 209 TF. And then this times that, which would be minus 2090. Right, 10 times that.
That would just be joules.
Yes, this would just be joules, and this would be, it's still be joules per degree C, because this is degree C, and we don't have a value in there to cancel that out yet. Then we come over here to this one. Let's see what this one is. 0.45, that's probably, I don't know, my brain's getting tired this afternoon, so I better calculate. 225. And that's joules per degree C. So this term would be that one times this one, 225 TF. And then this one would be minus 2025. Minus 2025 joules. Okay. Now we've got these two terms that have the unknown, so we have to combine those two. So that would be 434. Yeah, 434 T sub F minus 4,115. Yeah. Okay. Now, you could put this one on the other side, but that'd make them both negative. So we'll just put this one over there and then make them both positive. So this one equals 434 T sub F. Now T sub F is equal to this one divided by that one. Something went wrong. Let me do it again. My calculator's been messing up, so let me try that again. Did I do something wrong up here?
I upgraded the 0.45 times 50.
Yeah.
It's 22.5.
Ah, thank you. Yes, that makes sense. So that means 22.5 here, and that makes this 202.5.
I'm looking trying to get that one right. What is my right?
No, that's wrong.
90.
Yeah,
2025.
22.5.
I'm getting 2025. Because 1.45 times 50, right? Times the 90, 2025.
2025, yeah. 2025. So 2025 and 2090. Plus 4115. Okay, that's right. Then these two are the ones I messed up. That's wrong right there. There we go. So it's 209 and 22.5. All right. 231.5. Now this one divided by that. $17.8. I think they rounded it off to 18, didn't they? Okay. My calculator started messing up on me. This thing is old as the hills, so it doesn't surprise me. Oh, there it is right there. Okay. So that's how you solve a calorimetry problem. Everything is set to 0. You just have to be sure that the terms in here represent what's actually going on in the calorimeter. So before we get to that, let's say that we do know the calorimeter constant. What does the calorimeter constant look like? Okay, these guys right here are going to be S, mass, and then change in temperature, S, mass, change in temperature. This is water, this is iron. If we're going to take the calorimeter into account, right, then the form of the calorimeter is going to be a constant, big C, excuse me, times change in temperature, right? So you have to know the temperature before and after for the whatever's in the calorimeter, and that will tell you what this is for the calorimeter. So that means that if this is degree C, then this is simply joules per degree C. Mass doesn't enter into it, right? Because the calorimeter constant is determined for that particular combination of instruments in your device. Right? If you change one of them, like if you pull that thermometer out and put a different thermometer in it, you've changed this value right here. So once you determine the calorimeter constant, you can't change its structure. So how do we determine the calorimeter constant? Well, what we actually have is hot water, cold water, and calorimeter. So you have the same S for each one, and it's more convenient if you have the same mass. So you have like 50 grams or 50 mils here. And then you measure the temperature before and after and plug those in. And then you have also the change in temperature here, and this becomes your unknown. And you just solve for that one. That's your calorimeter constant. So we'll do that first before we do any of the experiments. Okay? I think I have an extra sheet in there that helps explain some of that. Hope it does. Let's see. Did I give that one to you?
There it is. That's just clarification of calorimeter constant calculations. Maybe I buried it in the... Yeah, it's the first sheet. Determine the calorimeter constant and calculations at the bottom. Okay, good. I won't leave you in the dark.
Okay. Now, Hess, I can't remember his first name, I think he was a German, took advantage of the fact that enthalpies are state functions. In other words, it doesn't matter how you get there. It's just the current state of the reaction. He took that concept and said, okay, if enthalpy is a state function, then I can take enthalpies from several other reactions and add them together. As long as those enthalpies represent individual reactions, that we add together for my final reaction, then each one of those added together gives me the enthalpy for my final reaction. The beauty of that is you don't have to do enthalpy calculations on every reaction in the universe. You just have enough of them so that you can combine the ones you want and determine what the enthalpy for your reaction is. Okay? You just have to be mindful of several rules. Here's an example. Now, this one tells you that the enthalpy for this reaction, nitrogen gas plus oxygen gas yields 2 nitrogen dioxide. And the enthalpy for that reaction is this, 68 kilojoules. Okay? Now, but this is just to prove Hess's hypothesis. We can combine this reaction, which we know to be 180 kilojoules, with this reaction, which we know to be minus 112 kilojoules, and we end up with this reaction. And combining those two, add those two together, you get 68 kilojoules. You get the correct reaction, and you get also the enthalpy. So let's see. There's one of these over here, nothing to cancel it, so that one comes down. There's one of these and one of those, so you got two of those. Okay, so we match that one and that one. And on this side, we've got two NOs here, but we've got two NOs there, so they cancel out because they're on opposite sides of the arrow. And then we have this one left over as a product. So yes, first condition of using Hess's law is the reactions that you combine into your target reaction have to add up exactly to the target reaction. Okay? If they do, then all you have to do is add up the enthalpies. Now, what happens if you have to, in order to make them fit and match the first rule, you have to maybe flip one around? What happens to this value? Just change the sign, right? Because it's going backwards. So now instead of exothermic, it's endothermic. Okay? What if you have to multiply the whole equation through by a constant in order to give you the right combination of reactants and products so that they add together to the final equation, so that they satisfy rule number one? Well, in that case, you just multiply the constant times this value also. The constant could be a whole number or it could be a fraction. You just multiply it by this value. We need to do an example, I think. See if we got enough time. Where are we in the, is S toward the end? Okay, S. And then okay. Yeah, okay, that's good. Just accidentally plugged it in. Okay, so let's take one. Oh, this is just an explanation of why Hess works. Since enthalpy is a state function, it doesn't matter how you get there, right? This is our target enthalpy, but we have to go here to that one, and then we have to come back down to this one. And the difference is just that, right? So the one-step reaction is the one, our target reaction, and the two-step is where we combine the reactions, and they've gone through this step and that step, and it doesn't matter, because as a state function, it doesn't matter how you get there. The path is irrelevant.
Hess's law illustrates why enthalpy is a state function.
For example, we want to determine the enthalpy change for the combustion of graphite to carbon monoxide. Imagine that the reaction takes place in two separate steps. Step 1 is the combustion of graphite to carbon dioxide. Step 2 is the decomposition of carbon dioxide to carbon monoxide. The net result is obtained by adding the two steps and canceling out like terms. The enthalpy change for step 1 is negative 787 kilojoules. The enthalpy change for step 2 is positive 566 kilojoules. Therefore, the desired enthalpy change for the net reaction is the sum of negative 787 and positive 566 kilojoules, or negative 221 kilojoules.
Now those individual reactions that are added together to the total, they can be performed. You just have to make sure the conditions are right that promotes the production of those products, and you can measure the enthalpy for those reactions. But when you change the conditions in such a way that the reaction takes place in one step, then, and you're proposing that reaction, but you don't want to actually do it, then you can take those individual reactions that have already been done, find out how much energy will be produced or consumed by the proposed reaction. That's good that you can do that. I mean, not just for convenience, but perhaps if you do those calculations and you find out the reaction is going to be exothermic in the extreme, then you'll want to take special precautions before you actually do it, such as the decomposition of nitroglycerin. Okay, so this is what I've said before. If the reaction is reversed, if you have to change the reaction, you flip it around, then you just change the sign on your delta H. If you need a different number of reactants and products, such that you multiply the entire reaction through by some constant value, then you use that same constant value times your enthalpy. Okay, so here's a... So what if we take ammonia and decompose it to nitrogen gas and hydrogen gas? Okay. Now, when we first started balancing equations, we were aiming for whole numbers, right? But this reaction is given with fractions, which is fine. It's given in fractions for a reason. But that would take too much time to explain right now. And this reaction, of course, is hydrogen and oxygen makes water. So it's going to be extremely exothermic, whereas this one's going to be endothermic. So can we arrange these in such a way that they give us this reaction right here? Can we add them together? Well, let's see. Ammonia here is a reactant, but it's a product over here, so that one's going to have to be flipped. Plus, we need 4 ammonias, right? So it's also going to have to be multiplied by a constant. Let's see. Water's on the wrong side for this reaction, so we're going to have to flip the water, this reaction also, to put the water on that side. Plus, we're going to have to multiply it by a constant to go from 2 to 6. So we know in advance we're going to have to do some major changes to these reactions, and that will affect these values before we even add them together. All right, so we're back to this one. So in this case, we have reversed the 2 reactions. So what this effectively does is put this product over here where it needs to be, put this product where it needs to be, puts this reactant where it needs to be, and puts this reactant where it needs to be. Notice that the hydrogens on this side will eventually cancel the hydrogens on that side, and they don't show up in the final equation. But we're not finished yet. We had to flip the equations and change the signs. Okay, we've done that. Now we're going to multiply them through by a constant. This one needs to be 4 so that we get 4 ammonias. So we multiply 4 times the enthalpy. And the next one needs to be 3. So we get 6 waters, which also gives us 3 oxygens, and 3 times the enthalpy. Okay. Now this is our final reactions before we add them together. And when we add them together, the hydrogen cancels, and we have the right amount of each one of the reactants and products. And then we can add these together, and that value is the enthalpy for this reaction. That's application of Hess's law. Now, why did those coefficients, why were they fractions? It has to do with the standard enthalpy of formation. Standard is what that little 0 means. That's a standard, whatever. If you see a little 0 up there, that means standard. And then the little f means formation. Okay, what are the conditions for the formation of a compound? The standard enthalpy of formation requires that you have 1 mole of compound. In this case, it was ammonia. Only the ammonia was over there. But for the standard enthalpy of formation, you need 1 mole of that. Then you take the elements from each of the elements in your compound and put them over here as reactants. Nitrogen and hydrogen. But they have to be in their standard forms at 25 degrees and 1 atmosphere pressure. Gases, remember, the temperature was 0 degrees standard. But for all other reactions, it's 25 degrees. So what are the conditions? What is nitrogen at 1 atmosphere and 25 degrees? It's diatomic. How about hydrogen? It's also diatomic. Okay? Now, you don't change this coefficient. That's always 1 mole. So that means you got to use fractions on this side. So you need 3 hydrogens. 3 halves. Remember we were balancing equations and we used that fraction rule? So 3 halves of H2 is 3 hydrogens, right there. Nitrogen, we need a half. That'll give us 1. That's why fractions, for standard enthalpies of formation. Okay? Oh, I left out one thing. If you have solutions that are involved, I can't imagine solutions being involved in this, but standard conditions, let's just say that, for any reaction. Standard conditions, 1 atmosphere pressure, solutions are at 1 molar concentration, and pure substances are marked as liquid or solid. Actually, gas also. Why we left that one out? Okay, and temperature is 25 degrees centigrade. I wouldn't want to work in that lab. Right, 20 degrees is 68 Fahrenheit. That's fairly comfortable. 25 degrees? No, that'd be another 9 degrees Fahrenheit. So 9 and 68 is 77. That'd be starting to get warm. Okay. So, what good would standard enthalpies of formation be? Well, if you know the standard enthalpy of formation for each of the reactants and products, then all you have to do is take the standard enthalpy of formation for the products and subtract the standard enthalpies of formation of the reactants. Now, in this case, here's the minus sign. Right? So instead of doing this one first and subtracting that one, they put this one over here because it's in order. Right? So that's negative minus 75 for this one. And this is another rule. All pure elements have an enthalpy of formation of 0. Okay. It's got to be a compound to have a value. So here's the carbon dioxide, and here's the water, and it would be this one minus these two gives you that value. If you know the standard enthalpies of formation, then all you have to do is add those up, subtract these, and of course, it's not just that, but the standard enthalpy of formation of water only includes 1 mole. So you would have to, this value represents 2 times its standard enthalpy of formation. That's a sorry slide because they left that out. That should be included. It should be 2 times whatever this is, and that's the consequence. This one's only 1, so that one's okay. This one's none, and that one's only 1. But this one is the consequence of 2 times the standard enthalpy of formation. Let's see if we got another one. We've already talked about that. Here we go. So here's the standard enthalpy of a reaction, and you take the products minus the reactants. And is everybody familiar with the sigma terminology? Sigma means summation. You add everything up. Right? So whenever you see sigma in a formula, that means you add everything up that's behind it. So in this case, you need the number of moles of the standard formation for the product. So if it's 1, it's just the value. If it's 2, you multiply 2 times it for each one of them. And for each one of the products, you sum them up. And then you sum up the reactants and subtract them from the products. That will give you the standard enthalpy for that reaction. Okay, so that's pretty neat too. Here's another one. All right, so for this reaction, we have sodium hydroxide here, and then we have hydrogen is 0, and then we have 2 waters. Well, that's the one for water, so you need 2 times that, and then that's for sodium. And the reason that is minus 368, notice that if you just take those together, you don't get minus 368. You have to multiply 2 times this one. And then 2 times that one. And this one, 2 times this one, minus 2 times that one, gives you that. Okay. All right, we talk a little bit about this. Right, what's a fossil fuel? Fossil means buried in the ground. Right? It's been there forever and we just discovered it. These are all fossil fuels. Any kind of oil, any kind of natural gas, coal, those are all fossil fuels. There are other fossil fuels. You could probably consider peat a fossil fuel. What else? I don't know if you consider uranium a fossil fuel. I guess you could. It's buried in the ground. You have to purify it before you can use it as a fuel. But we generally separate it out as nuclear energy. Then there's hydro energy, right? We put a dam across a river. We let the water build up behind it. So now the water at this level, if we take it from that level to this level, we can extract the energy from it. It's got potential energy due to position. And then wood, of course, is stored energy in the form of chemical bonds in the cellulose primarily. Nuclear energy is special. The stored energy in nuclear energy is in terms of mass. So nuclear energy, when you extract nuclear energy, you are converting mass into energy, according to Einstein's equation. Right? So you convert a little bit of mass before the uranium, and then the split products afterwards are lower mass, and that little change in mass is converted into energy. So that sort of flies in the face of thermodynamics, because we said energy can't be created or destroyed. Well, it really isn't. What we're saying here is that energy and mass are interchangeable. They're the same. That's kind of weird. This just shows you that the reliance of the United States on different sources of energy. So in the 1850s, we were burning wood. I mean, this whole continent was just covered with trees. They say you could walk without touching the ground. If you could walk from tree to tree or swing from tree to tree, you could go from the Atlantic Ocean out to probably maybe 100 miles west of the Mississippi River. Or actually, if you follow the river, Mississippi up through the Missouri River, you could stay on your trees and go all the way to the West Coast. You just couldn't go across the prairies because there's no trees. Until we cut them all down. There are still some old roads. In fact, there's one in West Virginia. A scientist showed it to me one time we were passing by. It was, what kind of tree was that? It was up, Morgantown, and you take the expressway east. That's 79. I don't know, but east of there, and you can see it from the freeway. Back in this hollow is an old grove of, not cypress. I can't remember what tree it is, but it was there, before Columbus. So in the 1900s, we started to rely more on coal. Right? And then in the 50s, we started to shift toward petroleum and natural gas. And in the 70s, we were really using lots of petroleum until OPEC decided to screw us. I remember when that happened. The gas prices went that just overnight. That's stabilized a little bit. We're using a little bit more coal now and a little less petroleum. So we got a more stable economy. Plus, the U.S. is now a net exporter of energy products, primarily due to fracking. We're able to access old, previously spent wells for oil and gas. So we go down and we frack them, and that opens them up a little more, and we can get more out of it. And we can access sources of energy that we couldn't even get before. So let's characterize the Earth's atmosphere. Most of the energy arriving at the Earth from the sun can penetrate the atmosphere. There are a few things that can't. Because of the upper ozone layer, some of the ultraviolet is stopped, it's absorbed. And that's good, because those are the dangerous rays. And what happens is, those rays reach the surface of the Earth, and if it's barren, of course, they heat that up, and then it re-radiates as infrared. If it hits plants, then the plants absorb some of it, but they reflect some of the others. Sometimes it's at an original wavelength, and sometimes they downgrade it to infrared. So you have this infrared being re-radiated from the surface of the Earth, and there are components of the atmosphere that absorb that energy and hold the energy in the Earth's atmosphere. The major component that does that is water vapor. By far, the major reabsorber of energy in our atmosphere is water vapor. Now, CO2 is a so-called greenhouse gas, but it's minor. It has almost no effect. Major effect, methane. Any methane in the atmosphere is much larger in its specific absorptivity of re-radiated energy. That's why, what's her name? Ocasio-Cortez. That's why she wants to kill all the cows so they'll stop farting. Did you see her Green New Deal? She put it up on her on their webpage or on her Twitter account. The Green New Deal. It says we need to do this. And when she started getting feedback about it and all the stupid ideas that they had, she took it down. Said, "Oh, that was just a draft." Yeah, right. We know you're a damn communist. And you want to take over the country and screw us all. So the jig is up, lady. But any reduction in carbon dioxide emissions will have almost no impact on the Earth's atmospheric temperature. Almost none. In fact, the models that have been used to predict a 10-degree increase over the next several years, decades, all those models failed. Not a single one of them works. I mean, the weatherman can't predict from 1 week to the next. And they're saying, oh yeah, we can predict 50 years down the line, 100 years down the line. After all, my name is Al Gore and I invented the internet. No. By the way, Al Gore got a D in his science class in college. Anyway, so some of the energy is trapped, and that's good for us, right? Otherwise, we'd be a snowball. But it's not due to carbon dioxide. It's due to water vapor. Water vapor is the primary reabsorber of energy that's trying to leave the Earth. And we got lots of it, right? Because 2/3 of the Earth is covered in water. So the hydrologic cycle is the primary driver of keeping the Earth warm. And then, of course, the amount of energy that we're receiving from the sun varies, right? Our orbit is not circular, it's elliptical. So sometimes we come closer to it, sometimes further away. And then the sun itself goes through cycles where it produces more energy or releases more energy into its system than it does at other times. So over the past 10 years, we've actually been getting colder. And who's to say that warming the Earth is a bad thing? Actually, it's a good thing. There's ample research to suggest that if the temperature of the Earth just went up by an average of 2 or 3 degrees, and we produced more carbon dioxide for the atmosphere, the productivity of the plants would double, right? Especially in the rainforest, where most of the productivity takes place. So we get increased food production as a result. And people would be able to live in farther northern latitudes without expending all the energy to keep things warm. So that's why they don't call it global warming anymore, because that idea fell through. Now they call it global climate change, right? And it's all our fault. You know, right? So new energy sources, all right? Converting coal, right? You can take coal and convert it to something that's less polluting, right? Because it does have pollutants that are involved. I mean, not CO2. EPA wants to call CO2 a atmospheric pollutant. That's ridiculous. Real atmospheric pollutants from burning coal, well, there's the dust particles that are produced. We generally trap those. There's carbon dioxide and water. That's a moot point. There's also sulfur. When you burn coal, you produce sulfur dioxide. Sulfur dioxide goes up in the air and combines with water and makes sulfuric acid. Now that can be a problem, particularly in, well, we've seen examples of it in the northern latitudes, in the New England states, where the western states are burning a lot of coal, and then this acid rain comes down and just sterilizes New York's lakes. That has happened. So we capture, we sequester the pollutants and do something with them. I don't know what they do with them. Of course, when we burn things in the internal combustion engine, those reactions the conditions are so extreme that you produce products that you don't want to, like oxides of nitrogen. If you have plenty of those, like in Los Angeles, then you can produce smog if the atmospheric conditions are just right. And that's bad for you too. Oxides of nitrogen and ozone. Right? Ozone's good in the upper atmosphere, right? But not down here, because it's extremely reactive. It's damaging to your lungs, to your mucous membranes. Right? So we need to keep ozone up there. Oil from shale, you can get that by fracking. Ethanol, that's a sore spot. The production of ethanol from corn, right, takes more energy to produce. A what would you say, a joule worth of energy of ethanol than it does that you get out of it. Right? So it's a net energy consumer to make ethanol. It wouldn't even be there if the government didn't subsidize it. Let's say, if you want more of it, subsidize it. If you want less of it, tax it. Right? So they need to tax ethanol out of existence. Besides, it's damaging to your engine. That's why we only have 10% in our gasoline, because most cars can't stand more than that. Methanol, I've never heard anything about methanol. Seed oils, biomass is potential energy source, but you have to learn how to convert it. You need special microorganisms that will convert it. And they usually end up producing methane. That's the most efficient. Easily, the infrastructure is already there for using methane, so that's why they go toward that. Okay, I think I've talked enough. And we'll do reviews next week plus the lab. So let's stop this.